Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 4, Electricity and Magnetism, and we're going to look at Inquiry Question 3, Magnetism. So we're going to be looking at this particular dot point here. We're going to conduct some investigation in terms of the magnetic field strength by wires and solenoids using these following equations. Okay. So let's get started. So for today's lesson, we are going to be investigating the magnetic field strength of induced conductors quantitatively. So we're going to look at this in terms of the numbers. And then obviously your success criteria is analyze the magnetic field strength of a solenoid and a straight wire conductor. For further reading, that's your textbook reference. Okay, so let's just quickly recall what we talked about before. Hans Christian Ørsted demonstrated that the flow of an electric current in a wire, that in the wire, when the current was nearby, the needle would change direction. So you can see in this apparatus that I have here, these two metal bars are connected to a power circuit. You can also see that when I turn on the circuit, the needle would point in a specific direction. So it's wobbling now. Once I turn it on, it sort of stays in this one direction, pointing in that way there, as you can see now. All right, next bit we can talk about is depicting magnetic fields. So if you recall, we said that a magnetic field lines, when they connect, represent an attraction. So when there is a connecting of magnetic field, we have an attraction force. If there is a null point though, we have a repulsion. So here we go in our example here, that is an example of an attraction. And now when north and north become aligned, you can see a nice little isotope lull point now forming here, okay? And it doesn't matter how close you pull the magnets together, they will still not be touching. I might make an additional short video on that one. Okay, so depicting magnetic field strength, we also said that depending on the quantity of flux lines being magnetic field lines, the density of those flux lines will dictate how strong the magnetic field is. So here we have a greater flux density, so it's a lot closer here. So I'll just write that down. So more flux, and also in this case, this spot here, we have greater flux density. So that means we have a strong magnetic field strength. We call the B field. Here we have a lower flux density, so we expect a lower magnetic field strength. Okay, let's actually look at the calculations when it comes to a straight wire conductor and then a solenoid. Okay, so in terms of calculating magnetic field strength, where these two gentlemen who did the experiment many years ago, and they found a couple of relationships when it came to a straight wire conductor and the overall magnetic field strength. They found that the magnetic field is perpendicular to the direction of the current. So if you recall your right hand grip rule for straight wire conductor, so just in case anyone forgot, let's show this via a simulation. If we have a electric wire, so this is our wire here, we said that with the right hand grip rule for a straight wire, the thumb, your right thumb that is, so try and picture that with me now, your right thumb is the direction of the conventional current. Now conventional current means it's going from positive to negative. What we remember from electric circuits, the longer hand of the power source is your positive current direction, and the negative component is the shorter hand. So the current is going, in this case, clockwise, okay? And then the way your fingers rotate around your right thumb will indicate the direction the magnetic field is going. Okay, so in this case here, I have my right thumb pointing up. So what that would represent is the fingers will be rotating anti-clockwise around the thumb. So if I use the right hand rule here, you can see my right thumb is pointing up. You can see the fingers are rotating around my right thumb in a sort of anti-clockwise component here. So that shows you, and you can see that's consistent with what we're seeing the magnetic field here. Okay, so just in case anyone forgot the right hand rule there. And as you could see there in that particular point, the direction of the current is going directly perpendicular to the magnetic field. The next one we have is the magnitude of the field is inversely proportional to distance. So we can see in our example that this one here. So as the magnetic field is really strong, the distance you are at that particular point to the magnetic field is really close. And then as you progressively get further and further away from the wire, the weaker the magnetic field goes. So this is showing our inverse proportional relationship there. We also know that the magnitude of the magnetic field is directly proportional to current. So as I increase the electric current of my wire, the magnetic field strength will also increase. So after all that, we get this little equation here. So 2 pi r, that's to represent the fact that a magnetic field will go in a radial direction. What do I mean by radial? I mean by circular. So you can see that the magnetic field that we're generating around the wire, they're all rotating in a circular motion. So that's where the 2 pi r comes from. And as you can see, if I'm looking at the direction of the current to the magnetic field, if my thumb is pointing directly up, the magnetic field is running at right angles in direction to where my thumb is. Okay, so that's what we're seeing here. You could even picture it as if your thumb was pointing directly out of the page. Okay, your fingers are wrapping around your thumb in sort of this direction here. Well, this is my left hand, but same idea. You can see that from where the thumb is, the direction of the current, and if I drew a tangent line for the direction of the magnetic field, that is directly at right angles to each other. So that's kind of what we represent by that. Okay, so this is the formula to calculate magnetic field strength for a straight wire conductor. Now this one, mu naught, let's quickly talk about what mu naught represents. Mu naught is known as the permeability of free space. If you did electrostatic force, you would have seen epsilon naught. So it has a similar idea, except this is implied for magnetic fields induced by an electric current in a vacuum. So the permeability of free space, you can consider it as the resistance a magnetic field experiences when it's being injected into a vacuum of space. The constant that we have is 4 pi 10 to the power of -7. The units we use to measure it is Tesla, milliamps, or Tesla. So I might just write that down. So the units to measure this is Tesla. In this case, we have meters. And then in this case, we have per amp or per ampere. If you ever notice, there's a little gap that obviously represents they're not connected together. If the symbols were connected together, then it would imply it's a milliamp. So, just for your own sake. Now, using this, we can actually work out the SI units, or the most appropriate units for the magnetic field strength. Some of you already probably know, but if we label all these out, the inverse amp minus amps, and then meters, inverse meters, you get Tesla. So Tesla is the SI units in measuring the magnetic field strength. It's named after Nikola Tesla, one of the very famous scientists that you know of as well, and obviously it's a car company nowadays. Okay, let's start with our first question. A long wire is carrying current directly upwards. Draw a magnetic field due to the current that's seen from top view. So if it's top view, so if I'm viewing it from up here, so that's where the eye is, I'm seeing that the current is coming out the page, so I get a little dot here coming out the page using my right hand grip rule. Okay, so your thumb is pointing directly at your face. Look at where your right fingers are curling. They are curling anti-clockwise, so they are going in this particular direction. Now remember, if I was to draw this for multiple lines, then it would progressively get further and further away. Well, this is an example of the best further and further away, but you know, not a great freehand draw, but that's the idea. So progressively further and further away. Okay, so that's what we have. And as you can see with the lines, they do go progressively further because that represents a drop in magnetic field strength. Okay, and then we have the solenoid. So if you actually look at a solenoid, it actually has a north and south component similar to a Bauer magnet, and you'll see if you put some arm filings next to a solenoid, you'll get a very similar magnetic field shape as well. So we can also actually predict the magnetic field strength of a solenoid based on a few key factors as well. So we can say that the magnetic field strength of the solenoid is dictated by the number of loops of wires. So if I have more loops of wires going around here, I'll have a stronger magnetic field. And this is actually how people make electromagnets that we use in everyday life. So that's actually this exact same application. As a matter of fact, if you grab an iron piece of nail, wrap it in copper wire, and then run some electricity through it, you have essentially magnetized copper nail, and you have made yourself an electromagnet. That's something we can also look into. All right, the magnetic field strength is inversely proportional to the length. So the longer the solenoid, the lower the magnetic field strength it is, or at least the ones that are wrapped by the wire. The magnitude of the field is proportional to the current, so the more electric current that's going through the solenoid, the stronger the magnetic field will be. Okay, so these are the two formulas we're dealing with. Remember not to confuse the formula for a straight carrying wire and a solenoid. Okay, your distance is going to be in meters. The length is also in meters. Might just write that down. So length. So length of exposure of wire or solenoid, and that's measured in meters. The number of turns, that's just, there's no value to that because that's just counting quantity, so you don't need units for that one there. Okay, so let's go through a couple of calculation questions. Calculate the magnetic field strength at distance 10 centimeters. So as always, make sure you convert your units. So 10 times 10 to the power of 2 meters. When we have a straight wire conductor of 10 amps. So the equation we're going to use is B is equal to epsilon naught. And then we have 2 pi r. And then we have our current here like so. Okay, so this is what we're dealing with. Epsilon naught is 4 pi 10 times minus 7 times our current of 10 amps divided by 2 pi times our radius. 10 times 10 to the power negative 2. So I'll leave that one there. We're going to sort out the answer in a second. Then our next one we have a y of 5 centimeters. What current must the y be carrying? So we have a magnetic field for this one, for our still straight wire conductor. We have epsilon naught times I, 2 pi r. So let's substitute all the values in first. 4 pi 10 minus I is the value we want to obtain. 2 times pi times 5 10 to the minus 2, that's what we want to get. So rearrange everything across, and our value of I will be the following. Let's go into the answers. So the first one we get is 2.0 10 to the power minus 5 Teslas. And then the next one we get is 1.5 amps. Okay, and that's how you do the response. Obviously, if you want to know the rearrangement of this one, you can always just check the answers. But that's how we do that. The next one we have is, again, for a current carrying wire. So calculate the magnitude of the current again. So if I just rearrange all the components already, so magnetic field strength times 2 pi r divided by epsilon naught. So magnetic field strength is 6 times 10 to the power of minus 7 times 2 pi r in this case 0.2 meters, divided by 4 pi times 10 to the power of minus 7. That's the working out there. We'll get to the answers in a second. And then our next question is to look at a solenoid. So magnetic field strength is 4 times 10 to the power minus 7. The number of turns we have is 400 times the current, which is 5. The length of exposure is 40 centimeters. So we need to convert that into meters. So that would be 40 times 10 to the power minus 2. That represents the meters. Okay, so that's the answer there. Let's go into the actual values. So for my value up here, I have 0.6 amps. For my next one, I get a value of 0.00628 Tesla. Okay, you could convert this and write it as 6.28 millitesla. That could work too. This way you're just leaving it at the SI units. So that's how you deal with that question there. Alright, so that concludes our lesson for today. Like we said, we talked about how to calculate the strength of a straight wire conductor and a solenoid, and then obviously we recapped on the right hand grip rule and stuff like that. So quite crucial that you understand how the right hand grip rule works. Hopefully this has been of help for you. If you do enjoy these videos, give it a like for support. Anyhow, until the next video, take care and have a good day.